Hello, everyone, and welcome to the webinar. As you all know, today's webinar will be talking about and showing you the multi-blade technology that we have inside of SolidCAM. The webinar today will be presented again by Ahmad Onkar, one of our product managers, and has also built a reputation of probably being one of our best presenters when it comes to webinars. And I'm sure this will be an extremely interesting webinar. So Ahmad, I will make you presenter, and you will be able to show your screen and go ahead.
Sydney.
Yes.
Hi, welcome everyone for this interesting webinar today. This webinar is going to be basically on multi-blade, and I'm going to talk about two parts today. First of all, the part that you're already seeing on the screen, which is a pretty simple multi-blade part, so we understand how the technology works, and then we move on to a much complex part that you've already seen in your invitation on the main page. Okay, multi-blade is basically a function of SolidCAM. It's a pretty easy to use function that helps programmers and users to generate cutting toolpaths for impellers and blisks easily. Basically, if you look at 5-axis engine itself, it's vast and it's complex and it needs a lot of input. What we did at SolidCAM was to get the inputs from different users on how these parts are machined and developed completely a new technology which is very easy to use and can be learned in less than 1 to 2 days on how to machine such complex parts. Right, so within our multi-blade technology, we've got roughing of the part. That means from raw stock, I would not say raw stock, I would rather say a turned stock, we create roughing toolpaths, and we also then go ahead and finish the blades, the main blade and the splitter, and then we address the fillet. In this particular part, the fillet is not that big, so if I go and evaluate and check the curvature, okay, the fillet is about roughly 1 hour. So it's not a major thing here. I could use a tool with a 1 hour corner radius, a taper ball nose with a corner radius of 1 hour, and I could be machining that particular fillet. But the next part that you're going to see has a variable radius. It varies from, I think, from 1 to 3 hour. So in such cases, finishing the fillet becomes very important. So we have got an option to directly finish the fillets. That's at the bottom. They are pretty complex, in fact. Machining fillets is really complex, so it's not very easy. And then we end up this part by finishing the floor or the hub part of the impeller. Okay. Now, to make things a bit simple during this particular webinar, what I have done is I have stored each technology as a template along with the tool that we are going to use. So I'm going to call in templates for roughing, template for finishing the blade and the splitter blade, template for finishing the fillets, and template for finishing the floor. Okay, just to make things simple so that I don't have to enter each values manually, but we are going to see each of them pretty deeply. So I'm going to apply operations from template, and I have a simple multi-blade. So I'm going to use a simple multi-blade roughing. I'm going to use this template name as the operation name. Okay. So what we have here in roughing, first of all, is a geometry. So I need to tell now to the multi-blade technology, what geometry am I trying to cut? Okay. What we're going to do here is we're going to have 3 different strategies. One is offset from hub, that is the floor, or offset from shroud. Now, what are the elements of these particular multi-blade that we are looking out at? First of all, This area that I just clicked is the hub or the floor. This is my blade surface. Even this is my blade surface, or anything associated with this is my blade surface. This small portion up here is my shroud. So I have a shroud, I have the blade surface, and I have the hub. Right, so I'm going to now select the blades, splitters, and fillets. So I just need to tell to SolidCAM what is my blade, what are my fillets, what are my splitter area. So I just pick the surface straight away. So what I'm going to do is I'm going to pick this region out here. So I'll pick 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are my 9 surfaces that I'm going to pick. Okay, sorry. Let's check if I have the faces here already. Yep, these are the 9 surfaces that I'm going to pick. So I'll apply that. My hub surface is this. Okay, and we are going to go offset from hub. We're not going to use the shroud and hub, but we're just going to say offset from hub. The tool that I'm going to use today is a taper ball nose with a corner radius of 2.5 R. This is how my taper tool looks like. Okay. Right. Levels. Basically, this is the page area where I have to enter the retracts and the type of retracts that I want. If you look at the whole page of retracts itself, most of the things are automatic. So I've selected I need to retract to an imaginary sphere, and the dimension and position are automatically determined by my multiplate technology. So I don't need to manually enter anything. In the toolpath parameters, I just have to check what is the tolerance that I want to work with. 10 microns tolerance is good enough. In the technology, I can put in the number of layers. That means the number of cuts I want between the blades and the number of slices. That means the depths that I need. Okay, so this is the depth and these are the number of slices. So what I'm going to do is the depth I'm going to use is 3 millimeters, and the maximum distance here is 2.5. That's my radius. All right. To the sorting, I want zigzag, and I want the cuts to start from the leading edge. Now again, there are some terminologies here. This edge here is called a leading edge, or the main edge from where the fluid or air, whatever you call them, will start getting in contact with the impeller, and this is my trailing edge. This one over here is my trailing edge. So I can ask the cutting to either start from the leading edge side or from the cutting edge side. So I'm going to start it from the leading edge, and I'm going to go from left, from here to right. So that's it's going to pan the cuts between left to right. Okay, edge rolling, I'm going to keep it to automatic. We are not going to set any values here because I want the software to help me to do that. Tool axis control is the biggest thing that probably you'll see in any 5-axis system, because that's how you control your tool in 5-axis. However, if you look at this page out here, you will see that the tool axis control is hardly anything. There are only about 6 to 7 parameters, and most of them, the defaults, they work very nicely. Unless you need to tinker here and there, the defaults work very nicely. Okay, now only thing I'm going to put here is my limits. I'm going to say my minimum limit is 0 and maximum limit is 91. I don't want the tilt to go more than 91 degrees, so I'm putting my limit at 91. Link, you can see that it's automatic. Majority of the things in multi-blade are removed. The control is removed from the user. Although he does have, for example, if I want, I can always override it. I remove the automatic, and I can do the things I want. But most of the times, automatic does the job for you. can say 99% of the time automatic does a job for you. It's that 1% of cases where you would like to control something, which we're going to see, of course, in fillet finishing, that we would like to control. That's where you override the automatic parameters. Gauge check. Since I've selected a set of blades, it's not necessary for me to put a gauge check because I've selected the area itself completely. Stock and transformation. Let's first look at how the toolpath comes up, and then we will rotate this toolpath. Okay, let's save this. And all I need to now do is, okay, let's synchronize. And let's hit the calculate button. This can take about 30-40 seconds to calculate because it's pretty quick. Right. So we have our first toolpath, which is pretty nice. You can see that it starts from the leading edge and it finishes also at the leading edge, and in between it runs the toolpaths. How would this toolpath look like in real world? So let's run the simulation in Solid Verify and check. That's my fixture, and let's run the simulation. Okay, you can see that we have completed the roughing. Looks pretty good. Right, now what we're going to do is I'm going to re-edit this toolpath again, and I'll go into transformation like I told you, and we'll just check how many blades these are. We have area 1, 2, 3, 4, and 5. So we have 5 areas. So I'll say 5 segments, and I want to machine all the 5 segments. I can say that I have 5, but machine only 3. Okay, so I can tell which segment to machine and which segment not to machine. So let's save this and let's calculate this. This is also going to be pretty quick because all it does basically is to just calculate one block or one area and then just apply the transformation to it. Okay, that's how my toolpath looks like, roughing toolpath. That's fine. Now once we have roughed out, I would now like to finish or semi-finish my blades because it's the same toolpath. So I would like to finish the blades. Now the finishing here is segregated into main blade finishing and finishing the splitter. However, we can do another thing. Okay, now this is something I had not planned, but I'm going to attempt it in front of you. We can have the machining of entire these 3 blades, one set in one go. How do we do that? Let's again add the operations from template, and this time it's simple finishing main blade, so I'm going to use that. Okay, and in the geometry, I'm actually going to pick the entire set here of all the 3 blades, and the hub here is this one. Here I'm going to go from hub to shroud, and that's my shroud. Stock to leave on the hub is about 0.3, and I would like to start, say, about 0.1 millimeter start offset. The tool remains the same. The depth of cut here is 1 millimeter, so I'm going to start at 1 millimeter. And I'm going to trim. What I'm going to do basically is, although this area is complete, I don't want the tool to travel on this edge here, so I'm going to trim at the trailing edge. That's what I'm asking the software to do, is to cut the toolpath at the trailing edge and join them by some link. One way, Tool access control, again nothing, because you'll see that most of the things here are automatic. Perfect. Let's save this. Okay. Synchronize. Let's calculate. $29 cuts. Take about 30-40 seconds more. Okay, calculation is done, and we have our machining. So what it has basically done here is, it started here, it's going all the way up here, machining, taking a nice blend and moving into the next part. So if I look at how the simulation happens, not the simulation, yes please, host CAD simulation, and this is how it's going to move. One finishes, go to rollover, next again rollover. So what it is doing is it's completely rolling over the entire 3 blades in one go, and then jumps up to the next pass. So finishing can either be done this way, or you could just copy this. You could finish blade by blade. So I'm going to paste it here, and instead of taking the entire 3 blades, what I'm going to do here is I'm going to just take one set of these blades, and we're going to calculate. Instead of finishing it together as a set, I could finish them individually, so it becomes easy for me to rotate it. Okay, calculation is done. What we have here is toolpath, and what is happening here is it's lifting and going there, because I have said it's a climb milling. So this is where I can actually change this. Instead of going to the clearance plane every time, what I can do is I can actually go and override it, and I can say link between layers. Instead of going to the clearance plane, I want you to blend or use a direct blend. Let's see the result. Okay, calculation is done, and you can see what happens here. Instead of going to the clearance plane, I'm making a join by taking a nice blending spline out of the part, so that I don't lift every time. It doesn't look nice. You actually end up spending more time by lifting and moving to the other side. So I can join them simply by blending a spline, and this I could do because I could override its automatic parameters. Right. Let's now add a toolpath for finishing the fillet. So I'm going to add operation again from a template. Already have made some templates. Fillet finishing. Okay. And what we're going to do is we're going to select the same set of surfaces. Okay. And the hub here is faces 1. Same tool. And in the technology, I want 8 cuts coming from the blade side and 5 cuts from the hub side. I can reduce it. I can say 3 cuts from the hub and 3 cuts from the blade side. And how am I going to do it? In sorting, I'm going to come from outside to inside. Okay, so I'm going to come from outside and gradually merge it to the center of the fillet, and it's going to be a one-way cutting. Okay, again, everything in tool axis is automatic, clearance is automatic. Let's calculate. What you're seeing here is the ease at which calculation happens, ease at which I'm able to select the geometry. I don't need to provide any kind of an input like a guiding curve, a guiding element, or anything like that. Let's see how this looks like. Again, we have retracts. You can see that 3 cuts coming from the hub side and 3 from the blade side, and 1 common cut at the center. So it's lifting up. Again, I'm going to override the between layers, and I'm going to use the direct blend. Let's run the calculation. So like I said, it's very easy to to program an impeller or blisk in this way. You can spend very less time in generating the programs, so it's very easy. Right, you can see that very nicely. I could just blend it out and join it to the next cut. So it's not that it's completely automatic and there's no user control at all. You're allowed to handle it. You're allowed to override certain parameters and make it machine the way you would like to machine it. Another very important aspect here is sometimes this face, the blade face, doesn't have a curvature. It's straight. In such cases, we recommend that you use a swarf cutting, just a single cut, and it works nicely. So you can actually add the swarf machining. Works beautifully on this. Let's pick the swarf surfaces. 1, 2, 3. 3 soft surfaces, and of course there is floor, and in the floor I've got the hub, and I've also got my fillet. Okay, this is my, I can pick the same tool, levels, surface normal. The surfaces will be detected using the normal, that's the outside direction. Okay, minimize rotation axis changes, and let's use a lead in and a lead out. So we have a default tangential lead in and a default tangential lead out. We're just overriding some parameters in it. Okay, let's save and calculate this toolpath. Now, many a times customer says, I have a very small curvature, but I don't really care. I just want it straight. In such cases, swarf allows you to do a degouging so that it doesn't gouge into the blades, but it will leave excess material in case of when it is a curved surface. So this is how my swarf would look like. Very simple, single tool path. Okay, now what you can see here is there is a gouge, which means that this particular surface is not exactly straight, so we will degouge it. Not a major issue, because what it's doing now is joining simply the upper and lower curves and generating the toolpath. So we can always go back and degouge the surface and just say, I just want to degouge. Calculate. Now, even in degouge, you have got an option of balance. That means it will try and balance how much it has to gouge and how much it cannot. Or I could help it by giving the gouge allowance, saying that you're allowed to gouge 10 microns, 20 microns, but not more than that. But in case of degouge, it will not touch or it will not gouge at all, which means that you could have material remaining on the blades after the machining is over. Okay, you can see that it was gouging earlier. Now it's degouged itself. So there is a possibility that it will keep material on the blades if the blades have small curvature. Okay, right. So if I look at a relatively simple impeller, it can be machined very quickly. You could have a part and probably a program out in less than 30-35 minutes roughing, because that's the most critical aspect of multi-blade machining, is the roughing itself. So quick programming, less fatigue on the programmer, guaranteed and reliable tool parts to machine on your 5-axis machine. All right, so let's look at another part. Now this part is a bit complex. Okay, so I'm going to open this part. And you can see that it's not an easy part. Okay, it has got a same geometry, but on the other side it's a mirrored geometry. And this obviously cannot be done on a simple 5-axis milling machine. It obviously will need a mill turn machine. So what I've done this here is I have chosen. So we have, let's open the machine simulation. I'll show you the machine, how it looks like. So basically, I'm going to cut this part on a DMG NTX 1000. Okay, so let's switch off the housing. Right. So I've switched off the housing, and this is how my machine looks like. So you've got this axis going plus minus 90. And then you have got another axis up here to rotate. Then we have our x-axis. Then you have the lower turret. You have the y-axis. And then you have Z1 and you have Z2. And then there is another one, Z3 and Z4. Okay, that's basically the door. And then you have the B-axis, B1 and B3, and then you have the C-axis, and then you have the C3 axis, the back spindle. Okay, great. So this is the machine I'm going to use. And what I have here is, so if I go into the setup, I have the upper turret main spindle, lower turret main spindle, upper turret back spindle, and lower turret back spindle. We are not going to do any turning in this, so it's obvious that I'm not going to use my lower turret at all. It's just going to be the upper turret main spindle and upper turret back spindle. Okay, so I already have certain paths generated, and that's basically my part movement from main spindle to the back spindle, which I don't want to do it during my webinar, so it's already done. And what I just need to do now is to add my tool paths. So you look at the part and you see that it's not a simple part, it's pretty complex. So I told you about the fillet. You can see that it's a variable fillet. So here the fillet finishing will come into play a lot, because I can't use a big radius, because I won't finish the smaller area, and if I use a smaller area, I won't finish the bigger area. Okay, so I'm going to add again from template, because I have made a template just to simplify the operation. So I'm going to add the complex. Okay, just go to save this. Just want to save this thing because I would like to move this up before I retract the upper turret. Okay, this is the place. Let's look at the geometry. So again here I have selected a set of blades. That means one splitter and two main blades. Perfect. And the hub, of course, is this one, faces one. I'm keeping a stock of 0.5 millimeters for finishing my hub and about 0.3 to finish my blades. The tool I'm using here is a 16 with a tip diameter 8 and a taper angle of 5 degrees. This is how my tool will look like. Again, a taper tool, taper ball nose. Let's go to level. Again, it's automatic, okay, because in this particular case we have a spear-like imaginary thing that is being placed on the part, and the retracts will happen to that particular imaginary spear. Technology, maximum distance 3, that's the depth of cut, and the step over is also 3 millimeters, just for the sake of our webinar. However, here I'm going to use a different technique of machining. I'm going to use the technique of offsetting the cuts from the hub, which are much more nice to see. Tool, parameters, tool axis. In this case, again, you can see that most of the things are default, and default actually works, like I said, in 99% of the cases. It works very nicely. You don't need to fiddle with that. Link between slices is automatic. Link between layers is automatic. No gouge check necessary unless and until you find that the tool is getting in contact with the side blade or something. Unless and until you don't get into that situation, be advised you not to use a gouge check, because it doesn't make sense since you've already selected a set of blades. In the transformation, however, I'm going to switch this off because since it's a complex part, it takes some time to calculate. Okay, so I'm going to save this. And what we're going to do here is I'll put it to calculate in parallel. Yeah. And while that is being calculated, what I'm going to do is I'm going to put my next process, that is the finishing, the fillet finishing, or rather the blade finishing. So let me add another operation from template. And what we are going to do is we're going to pick complex finishing main blade. That's the template that I've stored here. And let's use the template name. So what I have, my submachine, is that the part is going to be machined with a combination of the upper turret and main spindle. All right, let's go to the geometry. And here I'm not going to select a set of 3 blades because here it doesn't make sense. Because here it's completely one. I can't stop the tool, or rather it doesn't make sense for me to stop the tool at the trailing edge, because the trailing edge also needs to be machined. It's not on the outer periphery. It's inside, so it needs to be machined. So let's check another group of surfaces. So it's faces 4. That's the group of surface. Hub remains the same. And I'm going to use a shroud in this case. Let's check. Yeah, this is a shroud. So this upper piece is my shroud. I'll use that. Tool, I'm not going to use the earlier tool. I'm just going to use a new tool, which is a 12 millimeter with the tip radius of tip diameter of 4 and a taper angle of 5 degrees. Level is automatic. Technology, maximum distance 1. And here I did not trim it, but I said I want completely full, so I get an option to spiral the toolpath. No lifting, it'll just keep spiraling on the blade. Tool axis control, everything again is default. You don't need to touch unless and until you start getting some results that you're not happy. That's where you start adjusting with the tool axis. Otherwise, it's good to go. And what I'm going to do is I'm again going to calculate this in parallel. And by the time we have done with the finishing calculation, you can see that my roughing calculation is ready. Okay. So I can have a look at the simulation. So I'm going to go into my settings just to switch off. Verification is enabled. So I'm going to run my simulation, and this time we're going to see the machine simulation. Okay, so we will look at how the machine now behaves on this entire part. You can also see the machine setup, how the part has been set up on the machine, where the back spindle is, where your upper turret. Basically, we're going to use the upper turret and the main spindle. So the lower turret is not going to be involved at all. The lower turret will come into play only if there is a turning or a milling operation, simple 2D milling. Okay, the part is being loaded. Perfect. Let's switch off the design model, and this is how I have. Now, there are several things I could have done. For example, this is just for your information. I could have had a center, something like a center device, and that device would have been held in my back spindle, and I could have actually pushed my back spindle a little more forward somewhere here in order for me to hold the part, so that I don't, there is no cantilever kind of an effect now. But that's the theoretical side, rather the practical side. But here it's basically a demo, so we would like to see the features of multi-blade. So let me start with the machining. Let me increase the speed. It may not be that you will be able to see all the steps because you're using a GoToMeeting session, so it could happen that you see only some steps as it keeps updating the stock. Okay, so what I'm going to do is I'm going to push it completely till the end so that you see the entire result. Straight away. And while we are simulating, you can see on the left side the finishing has already been calculated. And we're about to finish the roughing simulation. It's pretty quick even on the machine simulation. Okay, the simulation on the machine is done, and this is how my blade looks like after it has been roughed out. So pretty much nice on the machine. Let's come out and have a look at the finishing toolpath. Okay, here I have used the transformation, so you can see that it finishes one blade, goes to the next, and then the next, and then the next, and then the next, and so on. So I've got a very nice toolpath even on this particular complex impeller. Again, I will add, create a template, and this time for the small blade, or the finisher blade, what we call. Exit, sorry, let's add operation from template, is a finishing blade. And the geometry here is the same. Pick the splitter. Yep, so this is the splitter blade geometry. The hub remains the same, and the shroud also is the same. It's faces 5. Tool, basically everything else is the same because I have used a template, and most of the things in multi-blade, the best part is that most of the defaults, they work very nicely in the entire machining. Okay, let me save this, and I put that for my background calculation, And I can straight away apply the next template, and this time for machining the hub. Okay, let's pick the geometry. That's the geometry, and the hub here is faces 1, face 7. Yeah, that's the hub. The tool that I'm going to use again is the same one, 12mm taper. Technology here, I'm going to use a maximum distance of 0.5mm, that's the step over. And sorting in this case is going to be zigzag, and we're going to go from left to right. It's almost like a roughing toolpath, but we are more focused on the floor. Okay. Right. Tool axis control. Again, everything is pretty much the same. Let's save this and put this in parallel while we just look at what happened to my splitter blade. And you can see that the splitter blade calculation is done. Very nice, clean toolpath. Okay, that's basically because this particular system has been written for really complex parts, and we handle these parts completely in a different way than we handle regular generic 5-axis parts, because these are specific. They are meant for certain application. So the way this entire system has been written is meant only to handle these parts. Means I can't use a multi-blade technology and then try and machine an engine port. No, we have another technology for it. So because it's being machined only for typical or a niche area, the system has been written in such a way that it can handle geometries in a much efficient way than we would do in the regular generic 5-axis, where we need to define a lot of supporting geometries to generate the toolpath. All right, so we have our hub finishing. Okay, very nicely done. The hub finishing is now ready. We'll also apply our simulation. Sorry. So what we're going to do now is I'm going to switch. Okay. Once we have finished the front side, I'll explain to you what happens next. Next is my upper turret retracts to the safe position because the front side finishing is over. Then the lower turret retracts, and then my back spindle jaws open up. It travels up to a certain point in rapid, and then beyond a certain point it travels in feed, and then the jaws close. Then the main spindle jaws open up, and then the back spindle drags the part back to its own position. So that's basically the gist of operations that we have done, and these are called as machine control operation. So I can add straight away another template now, and we can simply again use the front upper turret back spindle. Okay, coordinate system, here's Mach 3. Geometry, let's pick, not that. Yeah, faces 2, and the hub here is faces 3. Tool is the same. Okay, everything else here remains just the same. We don't change anything in this. I'm going to save this, and let's hit calculate. Okay, we'll just remove the transformation, otherwise we're going to have all the parts. This would take about a minute of calculation, so we'll have to be a bit patient here, because this particular part is a bit complex. It was not as simple as the earlier part. Somebody asked a question. In the meanwhile, I'll just take the question. Somebody asked a question saying that, is this a standard toolpath in 5-axis, or is it an additional module? Multi-blade is basically an additional module. It's not standard. Like I explained, this is not a generic 5-axis bundle. It's basically a completely different module in SolidCAM, and this is capable of machining only impellers and blisks, and basically it is to automate this process to a great extent. Okay, so it does only impellers, blisks, and parts like this. We've also seen some of our customers use it for machining gears on 5-axis. So if they have a spiral gear, a spiral bevel gear, so they use the multi-blade, because the gears basically have I mean, if you look at the geometry perspective, not the shape, but the geometry perspective, they also have something similar to blades. So we have some customers using the multi-blade to also machine gears. But the main function of multi-blade is to cut only impellers, blisks, and parts like this. And it is, of course, a completely different module. And the other thing is that you actually don't need to have your full-blown 5-axis to buy or to have multi-blade. You can have multi-blade completely separately. Okay, so we have the toolpath on the other side. So what we're going to do now is just to have a quick look at how the simulation works. So I'm going to switch off the stock control inside the simulation, and I'm just going to take the last toolpath and up to here, and this is what we're going to simulate. So let's go into machine simulation. So basically what we're going to see is that we're going to have the hub finishing and then the part transfer, and again roughing off the other side. Somebody again asked about the cost, but I'm sorry, I'm not the right person to answer you about the cost, because I have no idea about the cost. But if you can leave your email, I can ask somebody to get in touch with you, the right commercial person to get in touch with you, and they could provide you with an answer about the cost.
Yeah, you can probably get the information also from your local reseller. If you are a customer already, he can probably give you all the information you need about the cost itself.
All right. So you can see a couple of things that have happened. First of all, I have a problem here. That's because this machine, mathematically, it can go from either side. So we have got an option inside here in the hub finishing, is that I can use either the first angle pair or the second angle pair. In this case, this machine needs the second angle pair, so I'm going to calculate this toolpath again. Yes. So take about, again, half a minute or so. In the meanwhile, let's see if there are any further questions. Okay, that's answered already. I believe somebody has raised his hand. Okay. So while it calculates, if there are further questions, you could just put it in the chat area, and I will be more than happy to answer these questions for you. And by the way, the entire recording of this webinar will be available on our website by Friday. So if you want to have a look at it again, you could probably go back to our website and look at the whole webinar. So let's go all the way up to here. Simulate, machine simulation. This will take another 30 seconds because it needs, first of all, to transfer the part, the machine, post settings and the toolpath code itself to the machine. It's now outputting the last, that's the roughing, and then it will be loading up the machine simulation. Okay, the machine simulation is up. The part will come up and then the toolpath. Perfect. So we don't see the part, that's because I switched off the part earlier here. So let me show the part. Okay, that's good. So what I'm going to do is I'm not going to run this, but I'm immediately going to go to the next movement, that's the upper turret. You can see that, let's move to the safe position. And then the lower turret retracts to the safe position. And then the back spindle, rapid, feed, and the part is back up here. So it picks the part and moves up to the back spindle. Okay? So it's picked the part and it's taken to the back spindle, and then the head comes here and starts machining on the other side. So parts like these are done very easily using the multi-blade, and the most important aspect here is that I could use this multi-blade technology on my 5-axis or 9-axis mill-turn machine and cut such parts, including turning, milling, drilling, and 5-axis multi-blade application in one single environment without having to jump out of any system or move, close some window, open another window, nothing. Everything works in the same single window. Okay, and the best part is that multi-blade can cut impellers or blisks with splitter, with a single splitter, with double splitters, anything, because it's a system that's designed to machine impellers and blisks. So it's a very easy system. It's a very easy system to generate programs, reliable, safe programs for machining blisks and impellers. I come to the end. If there are questions, please ask me the questions. And there is somebody else also asking here. Somebody has asked me that the support for the 9-axis machine, for example, NTX 1000 is also an additional module. It's basically, if you have mill turn, and if you have bought the option of mill turn, then the mill turn option already is supporting the 9-axis options. But out of that, if you want to add the impeller module, it's an additional thing that you add on top of the mill turn module. Okay, so anything related to do with pricing and other things, please leave your contact so that somebody from our side can get back to you with much more clear information about the modules and pricing, because I'm not the right person to discuss pricing here. Right, so if there are further questions, I'm more than glad I could answer you. Please ask me. Sydney, I'm done with the stuff.
Yes, okay,
so there are no.
This is a webinar that I call multi-blade made easy, as we say. Okay, yes, thank you, everyone. Thank you, everyone, for joining the webinar. Again, Ahmad, fantastic webinar, very informative. And we'll see everyone again in our next webinar. And as Ahmad had mentioned before, this webinar has been recorded. And we will be making it available shortly. Within the next 2 days, you'll be able to see it on our website as well. All right, so everyone take care and have a fantastic weekend. Bye-bye.